When we started this course, we said that calculus was the mathematics of change. And we mentioned that one kind of change that you're familiar with is looking at the speed that you travel. When you drive, you compare the miles that you traveled to the time that you traveled to get your speed in miles per hour. So let's suppose you took a trip and you started your trip at noon and you ended your trip at 4 o'clock. And as you went along on your trip, you kept track of the time it was and how many miles you had traveled. So you might end up with a graph for your trip that looks something like this. What if we wanted to know the average rate of change on your trip from t equals 0 to t equals 1? So that means we want your average speed from noon till 1 o'clock. Now we know that to find an average rate of change, what we're looking for is the slope of a secant line connecting 2 points on a graph. So we'd be looking for the slope of this secant line. And since that secant line connects the points 0, 0, and 175, we can see that the average rate of change along that part of the trip would be 75 miles per hour. How about this part of the trip? We're going from t equals 1 to t equals 1.5, so from 1 o'clock till 1:30. Well, during that part of the trip, our time did change, but our distance didn't change. And that means that our average rate of change was 0 miles per hour, which makes sense. We didn't move any distance, so our speed must have been 0. And how about for the entire trip, the average rate of change from t equals 0 to t equals 4? Well, we can find that by finding the slope of the secant line between these 2 points at the beginning and the end of our trip, which would be 200 minus 0 divided by 4 minus 0, which gives us 50 miles per hour. So the average rate of change, the average speed we traveled on our trip, was 50 miles per hour. Now, does that mean we traveled 50 miles per hour on the whole trip? Not at all. Sometimes we drove faster, sometimes we drove slower, sometimes we completely stopped. But what if we change our question a little bit? What if we ask how fast you were traveling at exactly 2 o'clock? Now this gets a little bit trickier. And when we look at our graph and we think about how we found the average rate of change, the average speed over a period of time, we were looking for the slope of a secant line. If we're looking for a speed at a precise point, it's as if we just glanced down at the speedometer to check what our speed was. And in order to find that speed, to find that rate of change, we need to find an instantaneous rate of change, which is the rate of change at a point. Now you remember that to find the slope of a secant line through 2 points, we were simply finding the difference in the y-coordinates divided by the difference in the x-coordinates, the change in y divided by the change in x. We generalized that to say that if we had 2 points on our curve and we knew the difference between their x-coordinates, and we called that h, that we could describe the slope of that secant line using this difference quotient. Now let's look at a little animation to kind of figure out what's going on when we're trying to find instantaneous rate of change. So what you can see here is the graph of a parabola, and we have 2 points on that parabola that we've selected to find the average rate of change between those 2 points. Now you can see the secant line that contains those 2 points, and you also can see down toward the bottom the value of h, which is the distance between the x-coordinates of the 2 points. So right now, the first point has an x-coordinate of 4, the second point has an x-coordinate of 6.1, and we can also see the fraction that tells us the average rate of change from x equals 4 to x equals 6.1. So the slope of that secant line right now is just a little more than 3. Now if we move that upper point a little closer to the lower point, you'll see that a couple of things are changing. First of all, the value of h is getting smaller because h is the horizontal distance between the 2 points that define the secant line. And you'll also notice that the average rate of change, the slope of that secant line, is also changing. So let's just slide that point further and further down. This is like when we looked at the graph of our trip and we were looking at the endpoints of the time period that we were examining to find our speed during that part of the trip. But we were wondering what happens when we look down at the speedometer. What happens if we're looking for an instantaneous rate of change? So let's get these really, really close to each other. So h is 0.05 at this point. Our points are very close together. And look at what the slope of that secant line is right now. It's almost 2. So what do you think is going to happen when we put those points right on top of each other, and instead of having a secant line, we have a tangent line? Well, suddenly, we don't know what our average rate of change is. And that's because if you look at this fraction that we have 2 points that have really become 1 point, 4, 3, and 4, 3. And that means that this quotient that's giving us the slope has a value of 0 over 0. And that's an indeterminate form. We have no idea what that value is. Now we don't have a secant line here because we don't have 2 points to connect. But we can look at a tangent line to this curve. The tangent line touches the curve at exactly 1 point. And obviously, since there is a tangent line, it must have a slope. We just can't find that slope by subtracting the y-coordinates and the x-coordinates of 2 separate points because we don't have 2 separate points. The distance between the x-coordinates of these 2 points has become 0. So how can we find the slope of a tangent line when we're looking at a line that only touches our curve in 1 point? So to find the slope of the tangent line, what we'll do is use our difference quotient that we use to find the slope of a secant line. But this time what we're going to do is take the limit of that fraction as h approaches 0. Remember, h is the distance between the x-coordinates of the 2 points on our secant line. And if we make h very, very small, in fact, if we make it so small that it is almost 0, then we are in essence looking at 1 point on our graph instead of 2 that define the line. And that means we're looking at a tangent line instead of a secant line. So we will be able to find the slope of this tangent line that touches our curve in exactly 1 spot. Now this limit that we're going to be finding, that will find the slope of the tangent line, is called the derivative of our function at x. And that also means that this derivative that we'll find with the limit is going to give us that instantaneous rate of change in our function at x. Now notationally, we will write the derivative as f prime of x, and we're going to be using this limit to find the derivative. So let's look at an example. Our function is f of x equals x squared. We want to find f prime of x, which is the derivative of f. We're going to use our difference quotient in order to do that. And since our function is f of x equals x squared, we're going to use x plus h as our first input for f of x plus h. That would be x plus h squared. And then we'll subtract f of x. So we'll subtract x squared and divide by h. Now stop and think about something before we go on. We'd like to take the limit as h approaches 0, and this is a rational function, meaning it's a fraction. We said that we can find limits by direct substitution of rational functions if that function is defined at the value that we're trying to approach. And in this case, this fraction is not defined when h is 0 because division by 0 is undefined. So in that case, we're going to try to simplify the fraction to try to remove that discontinuity that we have in this function. So now we have a little algebra to do. We'll square the x plus h, and then in the numerator, x squared minus x squared are opposites. Now you still might be tempted to substitute 0 for h, but we're still dividing by h, so we still have something that's undefined at 0. But we can factor an h out of both the terms in the numerator, and we can simplify that fraction. So now we've got a function that is no longer undefined when h is 0, which means we can take the limit by directly substituting 0 for h, because h is approaching 0, and that means our limit is equal to 2x. So let's look at a graph of this function to try to figure out what's going on here. Our function is f of x equals x squared, so it's this parabola. And we've just said f prime of x is equal to 2x. You can think of that as a formula for giving the slope of the tangent line to this curve at any point on the curve. If we know the x-coordinate of our point of tangency, we can figure out the slope of that tangent line. So let's actually try that. Our function is f of x equals x squared. Our derivative of that function is 2x. What's the slope of the tangent line at x equals 1? So let's draw the line. There's our tangent line at x equals 1. We know that f prime of x equals 2x is a formula that tells us the slope of the tangent line at any point on this curve. We know that x is 1 at this particular point of tangency, so f prime of 1 will give us the slope of the tangent line at x equals 1. F prime of 1 is 2 times 1, which is 2. So all that's saying is that this tangent line, which is tangent to the curve at x equals 1, has a slope of 2. And if you look at the picture, you can see that. Slope is rise over run. The slope of this line is 2. Now, how do we find the equation of that tangent line? Well, first of all, we need to know the coordinates of that point. It looks like it's 1, 1, but let's be sure. We know that the x-coordinate of that point is 1 because that was given to us. To find the y-coordinate of any point on a graph, what we need to do is find the equation for that graph, which in this case is f of x equals x squared, and just use the idea of input-output. Our input's 1. Our output is also 1. 1 squared is 1. So, yes, indeed, exactly like it looks. That is the point 1, 1. So we know that 1, 1 is on our tangent line because it's also on the curve, and that's where our tangent line touches the curve. We also know the slope of that tangent line, which is 2. So we need to write the equation of a line that has a slope of 2 and that contains the point 1, 1. So let's go ahead and just use the point slope formula. It's not the only way to write the equation of this line, but let's go ahead and use that. We know that our slope is 2, so m becomes 2. We know that the point on this line is 1, 1, so x sub 1 becomes 1, and y sub 1 becomes 1. And if we rewrite this so that it's in slope-intercept form, sure enough, the equation is y equals 2x minus 1, which is exactly what it looks like from the picture. Let's use the same function. It's got the same derivative. And let's find the slope of the tangent line at x equals 2. So remember, the derivative gives us the slope of the tangent line at any point. So if we want to know the slope of the tangent line at x equals 2, we'll have to substitute 2 in for x for our first derivative. So f prime of 2 is 2 times 2, which is 4. So the slope of that tangent line is 4. What if we want to write the equation of the line? Well, then we have to know what that point of tangency is. And so far, all we know for sure is that its x-coordinate is 2. The y-coordinate of that point we can find by substituting 2 into our function, because our function gives us points on the curve. So 2 squared is 4. So our point of tangency is 2, 4. And now we want to write the equation of a line that goes through 2, 4 and has a slope of 4. And the equation of that line would be y equals 4x minus 4. So that's generally what we'll do anytime we want to find the slope of a tangent line to a curve. We will take the derivative of the function, and that will give us a formula for finding the slope of the tangent line at any point. If we want to know the slope at a particular point, we'll substitute the x value of that point of tangency into our derivative. And if we need to know the equation of the tangent line, we'll need to find the y-coordinate that goes along with that x-coordinate we were given. And then we can use our point slope formula to write the equation of a line. And let's find the derivative of this function, f of x equals 5x plus 1. So we're going to have to substitute x plus h into our function to find f of x plus h. And then f of x is 5x plus 1. We'll have to divide that by h and then take the limit as h approaches 0. Now once again, we're dividing by h, so we can't take the limit until we've simplified this fraction completely and that h that's in the denominator has canceled out with a factor of h in the numerator. So we have some work to do. We'll distribute the 5, and then we've got some like terms that are opposites, 5x minus 5x and 1 minus 1. And now we've got a factor of h in the numerator and denominator that we can cancel out. And we have the limit as h approaches 0 of 5. Now this looks a little funny because at this point we need to substitute 0 for our h's, and there is no h, so that means the limit as h approaches 0 of 5 is just 5. Now stop and think about this one for a second. This one may seem a little bit strange. Our function was f of x equals 5x plus 1, and that's a line. And what we were being asked to do is find the derivative of that, which means find something that describes the slope of the tangent line to that line. And the tangent line to that line is actually the line itself. So since that line has a slope of 5, it's not surprising that the tangent line to that line also has a slope of 5. There are going to be functions that have places where we cannot take derivatives. So this is the first case. We cannot take a derivative. A function is not differentiable. That's another word for a derivative. A function is not differentiable at a point, x equals a, if there's a corner at a. So all of these points that are in red are corner points for their functions. We would not be able to take a derivative at those points. A function is not differentiable at a point x equals a if there's a vertical tangent at a. So at this point that's in red, we would not be able to take the derivative at that point. It probably makes sense, after all, if the derivative tells us the slope of a tangent line, that's a vertical line, and a vertical line has a slope that's undefined. And the third thing that we can't do is we can't differentiate, we can't take a derivative at a point, x equals a, if our function is not continuous at a. So in this case, we would not be able to take a derivative at x equals -2. Now, one more thing about notation. The notation that we have seen so far is that if our function is written like this one, f of x equals x squared, then to describe the derivative, we say f prime of x. We also know that functions can be written just in terms of x's and y's. So f of x equals x squared could just as easily be written as y equals x squared. And if that's the case, if that's the way we chose to write our function, then the way we'll write the derivative is what you see on the right side here, which is the derivative of y with respect to x. So it's just a different way to write a derivative. Sometimes instead of saying the derivative of y with respect to x, sometimes we get a little bit of a shorthand with that, and you'll hear us just say dy dx, which still means the same thing. It's just a different notation that still means derivative. Now, using that fraction and taking the limits is a bit of a long way to find a derivative. It's something that you need to know how to do, and it's something that you're going to be practicing. But there are some differentiation techniques that will shorten that process. The first of those techniques is using something called the power rule. So this is what the power rule looks like. For any real number k, the derivative of y with respect to x of x to the k power equals k times x to the k minus 1 power. So what that means is if we have x to a power and we want to take the derivative of that, all we have to do is bring that power down front and multiply it times x to 1 less power. So let's use that power rule on each of these functions. First one is y equals x to the 5th power. So the power rule says if we want to take the derivative of this, all we have to do is take that power of 5, bring it down front, and multiply it times x to 1 less power. So the derivative of y equals x to the 5th is 5x to the 4th power. For the second one, y equals x is our function, and we can use the power rule on this one, but it may not be as obvious because we don't see a power. But there is a power there because x has an implied first power, which means to take the derivative of it, we can bring the 1 down front times x to 1 less power. 1 minus 1 is 0, and x to the 0 power is 1. So we really have 1 times 1, which is just equal to 1. And the last one, y equals x to the -4th is our function. Because we have x to a power, we can use our power rule, bring the -4 down in front, take that times x to 1 less power, and we'll see that our derivative is -4 times x to the -5th power. Now, sometimes the power rule is a little bit hidden in these problems. That's the case with this one. We want to differentiate y equals the square root of x. What you need to remember is that the square root of x is the same thing as x to the 1/2 power. So, if we think of it that way, we can take the derivative of x to the 1/2 power by bringing the 1/2 down front, times x to 1 less power. So 1/2 minus 1 is -1/2. Now you may remember that we don't like to leave expressions with negative exponents. They're not considered simplified. So we could rewrite this as 1 over 2x to the 1/2. Now, one more rule that's actually related to that power rule, but it's not obvious, and that is that the derivative of a constant is 0. So if we wanted to differentiate y equals 7, all we'd have to notice is that 7 is a constant, so we have a constant function here. So the derivative of that constant function is just 0. Now the reason why a derivative of a constant function is 0 is that a constant function represents a horizontal line. And since a horizontal line has a slope of 0, the slope of any line tangent to that horizontal line is still that same horizontal line. So a tangent to that horizontal line still has a slope of 0. Another useful rule is to know that the derivative of a constant times a function is the constant times the derivative of the function. So if we wanted to differentiate something like y equals 7x to the fourth, 7 is the constant times the function, which is x to the fourth. So the derivative of this function is 7 times the derivative of x to the fourth. And since x to the fourth is x to a power, we can use our power rule on x to the fourth. So that's 7 times 4x to the third, which is 28x to the third. Once again, sometimes to use these rules, you may have to rewrite what you're looking at in order to make it fit into the rule. If we want to differentiate y equals 1 over 5x squared, we're going to need to think of that 1 over 5x squared as 1/5 times 1 over x squared. That means we'll be able to use the rule we just saw. We have a constant times a function, but then we also need to think of the 1 over x squared as x to the negative second power so that we can use our power rule. So to take this derivative, what we're going to be doing is taking 1/5 times the derivative of x to the negative second power. And the derivative of x to the negative second is -2 times x to the negative 3. And if we want to write that so that we have a positive exponent, that would be -2 over 5x to the third. One more differentiation technique to talk about today, and that is the sum difference rule. Now this is going to look really complicated when you see it, but it's not as complicated as it looks. The sum rule says that the derivative of a sum is the sum of the derivatives, and the difference rule says the derivative of a difference is the difference of the derivatives. What that means is if you have a function that's made up of several terms, you can take the derivative of the terms separately and then add or subtract to put those back together for your derivative of the entire function. For example, if you want to take the derivative of 5x to the third minus 7, we have two terms here, 5x to the third and minus 7. So we can take the derivative of those terms separately. And then in the end, we'll just put them together through subtraction. So the derivative of 5x to the third is 15x squared, and the derivative of 7 is 0. So the derivative of 5x to the third minus 7 is 15x squared. This one has three terms, so to find the derivative, we'll take the derivative of each term separately and then put them back together with subtraction and addition. The derivative of 24x is just going to be 24. In order to take the derivative of the square root of x, we'll have to think of it as x to the 1/2. And in order to take the derivative of 5 over x, we'll have to think of it as 5 times x to the negative first. So we'll use the rules that we've already seen to take the derivatives of those separate terms. Derivative of 24x is 24. The derivative of the square root of x is 1/2 x to the negative 1/2. And the derivative of 5x to the negative first is negative 5x to the negative second. Now we can rewrite each of those terms if we do not want the negative exponents, so that the x to the negative 1/2 is down on the bottom of that fraction as the square root of x, and the x to the negative 2 is on the bottom of that last fraction as an x squared. Now what you've probably noticed is that There's really two things that are going on in the last problems we have. One is that you have to know how to use these new derivative rules, and the second thing is there's a lot of algebra involved in simplifying. So you'll get a chance to practice all of that in class, and hopefully you'll get up to speed on the algebra part of this pretty quickly.